Okay, we're going to start on chapter 4, reactions in aqueous solutions. And there we go. So, first topic we're going to talk about is electrolytes and non-electrolytes. Strong electrolytes and weak electrolytes, and how do you identify an electrolyte? So, we're talking about solutions. They're a homogeneous mixture of two or more substances. They can be gas. Air is a solution, it's a mixture of gases. They can be solids. You think of alloys like brass. And they can be liquids, such as salt water. You can also put things such as a liquid in a solid. So we have mercury, which is a liquid, dissolved in silver to make what's called an amalgam. And does anybody know where we find that? Tea, fillings. Yeah, the old silver fillings. So when we talk about solutions and definitions, the substance is present in the largest quantity. It's called the solvent. Stuff in the smaller quantity is called the solute. Now, although we can have different types of solutions, gas, solid, for this chapter, we're just talking about aqueous solutions, solutions in water. So an electrolyte is something that dissolves in water to yield a solution that conducts electricity. A non-electrolyte, when dissolved in water, does not conduct electricity. So I think we've talked about electrolytes in here. Have we not? A little bit about, think about Gatorade, sports drinks. Okay. So as we hear the term electrolyte, oh, Gatorade, Sportade, Powerade, it's full of electrolytes. Well, if we go back to a little bit of anatomy and physiology, I hit my leg and I go, ow, why? My leg's down there. My brain, despite what other people think, is up here. Nerves. So at the junction of the nerves, there are things called synapses. So how does the message go? What? Electrical impulses. So at the synapses we have are called channels. You might have heard of sodium channels, potassium channels, calcium channels. So we have ions, sodium ions, calcium ions, potassium ions. So those ions, because they're plus and minus, chloride ions and that, how do you get plus or minus? You do what? Ionic compounds involve what? Charges, but how do you get the charges? The sodium goes to positive, the chlorine goes to minus. What does the sodium do to the chlorine? The what? I know it balances, but how do you get the charges? No, you're not sharing. Ionic is a... You can fight me here. Ionic is, get a positive, what do I have to do? No. Become positive, what do I have to do? I have to lose an electron. So if you get a negative, I have to gain an electron. So it's sodium chloride, sodium positive, chlorine minus. So what happens? Sodium does what? Gives its electron to the chlorine. So it transfers electrons. We call that normally, in your house, electricity. Oh, okay. So you're out working a lot in the sun, running and that, and you get all sweaty. When you come in, the sweat dries, you got this white stuff on your shirt. That is Salt. Where'd it come from? Come from the salt berry. Where'd it come from? Came from your body, right? From the sweat came out of your body. So you remove sodium, chlorine, potassium. So you're removing ions. So you think about your nerves. To transfer the electricity, you have to have those ions. So now you've depleted those ions. Outside of transferring pain signals, what else do nerves do? Well, not only that, but they cause something. How'd you get here? Yeah, so how'd you walk? What made you walk? Muscles. Doing what? Contracting in there. So the nerves send signals to your muscles to contract. So when we sweat and lose a lot of ions, those little synapses don't have enough ions, they start short-circuiting. Anything happens to our muscles? They cramp. So I see, especially now you're watching college football or professional football now, it's August, it's about September, but it's still hot. And the players go out the field, they have muscle cramps. Because they've lost sodium and potassium. So they usually go and they drink Gatorade, which replaces that. Or in my days, we eat salt tablets. Or if you want to replace potassium, you eat a banana. In severe cases, they'll actually put an IV, a saline IV, in you to replace those electrolytes. So an electrolyte, we look at two substances here. Top one, C12H22O11, is table sugar. You put it in water, it dissolves. It stays at C12H22O11. It doesn't come apart. They call that dissociation. It doesn't dissociate. Sodium chloride, on the other hand, in water comes apart, dissociates into Na plus and Cl minus. So now I have two ions, positive and negative. Because I have two ions, I can now transfer electrons. I can conduct electricity, hence they're electrolytes. Sugar doesn't dissociate. Sugar is a non-electrolyte. So if I'm standing in distilled water, ultra pure distilled water, and someone throws a plugged-in radio in there, I'm fine. Water's not going to conduct electricity. You put sugar in the water, still not going to conduct electricity. A teaspoon of salt, I'm dead. That's going to conduct electricity. And unfortunately, that's what happened to that poor little lifeguard in Raleigh. It just turned out that the pump failed, and the pump, when it failed, there's supposed to be a grounding wire, and the grounding wire was broken. So instead of the electricity going into the ground, you had to go on the other path, which was across the pool water. And she reached into the pool water, that's it. So dissociation, which is what I said, is the process by which an ionic compound, upon dissolution, breaks apart into its constituent ions. So if we're talking about ionic compounds, they dissociate. Now molecular compounds, on the other hand, covalent, form ions when it dissolves. So HCl, hydrogen chloride gas, in water, will give you H plus and Cl minus. So again, in either case, we have ions and we can conduct electricity. Acids are molecular compounds that are electrolytes. We just talked about HCl. HCl gas in water is hydrochloric acid, so that's an electrolyte. You can have molecular bases. So ammonia gas in water gives you this NH4 plus and the OH minus. So again, we have a plus and a minus. It's an electrolyte. Conduct electricity. So a compound that dissociates completely is known as a strong electrolyte. So most of your salts are strong electrolytes. So all water-soluble ionic compounds dissociate completely upon dissolving. So they're all strong electrolytes. So baking soda is a salt. Dissolves completely in water. It's an electrolyte, strong electrolyte. So here's a list of strong molecular electrolytes. You see most of them are acids: hydrochloric, hydrobromic, hydroiodic, nitric acid, chloric acid, perchloric acid, and sulfuric acid. So they're strong electrolytes. Sulfuric acid, I mentioned what time is found where? Car batteries. Wouldn't it make sense you would want something that can conduct electricity inside a car battery or inside any battery? So you need an electrolyte. A weak electrolyte is a compound that does produce ions when it dissolves in water. However, it doesn't dissociate completely. So the one we're looking at here is acetic acid, which is a liquid. If I dissolve that in water, i.e. make vinegar, 5% solution, I get the H plus and the acetate anion, but you notice there's a double arrow here. There's not a single arrow. That means the reaction goes both ways. However, it stays mostly as the undissociated acetic acid. It only goes to the right about 5%. And later on, if you do CHM152, you see why that happens. So it's a weak electrolyte. It conducts electricity, but not as much as a strong electrolyte. One thing to notice with ammonia, it doesn't dissociate. It makes the water molecule dissociate. It ionizes a water molecule. So the NH3 takes an H plus from the water to become NH4 plus, and leaves behind the hydroxide, the OH minus, anion. And later on when we talk about acids and bases, we'll learn what's going on with that. So here's a pictorial example. So here, the one on the left, if I have water, either pure water, or even like sugar water, the light bulb's not going to light up because there's not an electrolyte. If I have a weak electrolyte, which would be the middle one, you can see it's kind of a dull yellowish light. But if I have a strong electrolyte, where everything ionizes, I get a nice bright light. Now your tap water contains a lot of electrolytes. Got a lot of minerals in there, a lot of salts, and it goes through the pipes and that. So yeah, you'll get zapped real good. So how do you identify electrolytes? So first, look to see if it's ionic or molecular. So if it's ionic, we know we got to have what? A metal. So that's going to have a cation. The metal forms the cation. It can either be the metal or the ammonium ion. And an anion, which may either be an atomic or polyatomic anion. So a binary compound that contains a metal and a nonmetal is almost always ionic. And any ionic compound that dissolves in water is a strong electrolyte. Now, not all of them dissolve in water. We'll talk about solubility later on. If it doesn't contain a metal or the ammonium ion, it's molecular. If it's molecular, you need to determine if it's an acid. How do you do that? Well, you look at the formula. Formula for acids, usually the ionizable hydrogens, the ones that will come off, are written first. So hopefully they give us some examples. Oh, here's a flow chart. So if it's ionic or molecular, if it's ionic, it's a strong electrolyte. If it's molecular, is it an acid, base, or neither? If it's a base, it's a weak electrolyte. If it's neither, it's a non-electrolyte. So table sugar is neither an acid or base, so it's a non-electrolyte. If it's an acid, if it's one of the 7 strong acids listed in table 4.1, it's a strong electrolyte. If it's not, it's a weak electrolyte. So HF, hydrogen fluoride in water, you would think would be strong electrolyte, but it's not. It's not one of those 7 listed. So hydrofluoric acid is actually a weak electrolyte. So methanol, let's look at this one. Non-electrolyte, weak electrolyte, or strong electrolyte? Is it ionic or molecular? Molecular. It's not an acid. It's not a base. So therefore it's neither. It's non-electrolyte. What about sodium hydroxide? Ionic or covalent? Ionic. It's what? Well, you got a metal, so right away, you know, does sodium hydroxide dissolve in water? Sodium hydroxide lie? Yeah, so we're going to get a stronger weak. Okay. Ethylamine, that's kind of hard when you don't know any organic chemistry, is a weak base. It will dissolve in water, so it will be a weak electrolyte. HF, which I already told you, it's not one of the 7 strong ones, so it's a weak. So what do we have here? Methanol, non-electrolyte. Sodium hydroxide, strong electrolyte, so far we're good. Ethylamine, a weak electrolyte. HF is also a weak electrolyte. Okay. So we said for strong electrolytes, the ionic compounds have to be soluble in water. How do you know it's soluble in water? Well, there's guidelines for it. So an insoluble product that separates from a solution is called a precipitate. Chemical reaction in which you form a precipitate is called a precipitation reaction. So if I put 2 solutions together and I see a solid form, that's a precipitate. The solutions can turn cloudy, turbid, and we'll probably do some of those. I don't think we did any yet. So here we're seeing a solution of sodium iodide. You can see the beaker on the left there is clear. In the other beaker, colorless solution of lead nitrate. We mix them together, we form lead iodide, which forms is solid, not water soluble. So you get this yellow, bright yellow precipitate. It just falls out of solution. What's left in solution are the Na plus and the NO3 minus ions. That's all well and good, but how do we know what's going to happen? Well, when an ionic substance such as sodium chloride dissolves in water, the water molecules remove the individual ions from each other. It's a process called hydration. So if I look at this, and I look at NaCl, and we put it in water, we have the Na plus and Cl minus. Well, if we evaporate the water, we end up with what? We end up with the salt that we get because the Na plus and Cl minus. What keeps them from coming back in the first place? Well, once we put them in the water and they start separating, the water molecules surround them. So they each get surrounded by water molecules. I'm not going to draw all of them. So that keeps them separate from each other. So they don't really see each other, so they're not. Now when you remove the water, they all come together. And there you see it in a much better rendition than I can draw on the board. So you see the plus in the middle there, that's the sodium cation surrounded by water. And the negative is the chloride anion surrounded by water. And you notice the water molecules are facing different ways. That's because water is polar, which we'll get into later. So it turns out that, okay, I just dump a teaspoon of salt into a glass and I stir it, it dissolves because the water molecules surround it. So I got some more salt, the water molecules surround it. I keep adding salt. After a while, I'm running out of water molecules to surround it. So now the Na plus and Cl minus really can't get far apart from each other. So what happens? It what? It just stays in the bottom, it doesn't dissolve. So I've reached the solubility level of the water when I can no longer separate. So solubility is defined as the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. So, you know, if I'm going to make rock candy is just basically sugar. The recipe is to take 4 cups of sugar, dissolve it in 1 cup of water. So I take 1 cup of water, throw in 4 cups of sugar, and I stir it. I'll be dead before it goes to the solution. So what you do is you take the water, get it on the stove, almost boiling, you start adding the sugar little by little. Eventually, it'll all go in. And you have a nice thick syrup. That makes it real viscous. Very carefully, you pour it into a jar, something like that, hot and sticky. And you take a pencil or something, tie a string to it, hang it down in the solution. As it cools, the solubility is going to go down. So it's going to start to crystallize out of solution. And it'll tend to crystallize on the string, and the slower it cools, the bigger the crystals are. And then you get these crystals, these faceted crystals. Looks like rock, well, it's rock candy. And if you add flavoring to the sugar solution, it will come out whatever flavor you want. You can't do that with all ionic compounds. So here's part of the table. If your compound contains an alkali metal cation, so any of the column 1 cations, or the ammonium ion, it's water soluble, no exceptions. If your compound contains the nitrate ion, the acetate ion, or the chloride ion, it's soluble, no exceptions. If your compound contains the chloride or bromide or iodine ion, it's soluble, except if you're talking about silver salts, mercury 2 salts, or lead 2+ salts, then they're insoluble. Compounds containing the sulfate ion are soluble, except the silver, the mercury, the lead, the calcium, the strontium, or barium. Those are insoluble. Well, there's more. Compounds containing the carbonate anion, the phosphate ion, the chromate ion, or sulfide ion are insoluble, except if you have one of the column 1 cations or the ammonium ion. Compounds containing the hydroxide ion are insoluble unless you have one of the column 1 cations or barium. So barium's in column 2, so if I have BaOH2, that's water soluble. MgOH2, on the other hand, is not. And we find Mg, magnesium hydroxide, in go to the grocery store, the drugstore, Phillips, milk of magnesia. That's what magnesia stands for, magnesium. And if you look at it in the bottle, what color is it? Why is it white? Can you see through it? No, so it's not a solution. We're doing that. It is a suspension of magnesium hydroxide in water. If you find a really old bottle of it, you'll see it's clear all the way down to the bottom, and there'll be a big white mess at the bottom. What does it say on the bottle to do before taking it? Shake it. So you make sure you get it evenly distributed. Otherwise, you're not getting what you paid for. If you get the bottom, then you're getting too much what you paid for. Silver nitrate, soluble or insoluble? Well, what two ions are we dealing with? We're dealing with silver, Ag+, and the other one we're dealing with is nitrate, NO3-. What do we say about nitrate compounds? They're water soluble, so that is water soluble. Calcium sulfate. You say it is what? What about sulfates? They're what? Okay, what are the exceptions? Calcium, one of the exceptions? Oh, so now that makes it insoluble. And potassium carbonate. K is in what column? Column, in periodic table, it's in column 1. What did I say about all column 1? They're soluble. So A is soluble because right there it says on the second group there, the nitrate ion They're all water soluble, no exceptions. B was insoluble because even though sulfate are water soluble, one of the exceptions is calcium. So you got to look at both the anion and the cation and see what's hit the button too much. I should say C is soluble. I don't know why they made that B again, because they did B twice. Yeah, B is insoluble. C, that should be solution C, is soluble. And you can see carbonate is insoluble, but potassium is one of the exceptions. Because if you think of calcium carbonate is commonly limestone or chalk. And as far as I know, chalk is insoluble. Limestone is insoluble. So now we're going to talk about equations here, molecular equations. Everybody see the front of the board here when I write? That better? I'm never sure. So here we're going to look at the molecular equation, which is just like we would normally write it. So we have lead nitrate, aqueous, plus sodium iodide aqueous goes to, what did I get there? Sodium nitrate aqueous plus lead iodide, and you notice it says solid. So right away, if I look at that reaction, this is I'm taking two solutions, putting them together, and I'm going to get a precipitate of lead iodide, because it's a solid. But you have to remember, when I put these two solutions, if I have a solution of lead nitrate, I don't have lead nitrate, I have Pb2 plus and NO3 minus. Kind of floating around, both ions, they're associated. Sodium iodide, I have Na plus floating around and I minus floating around. So they're all interacting with each other. So if the lead gets together with another nitrate, nothing happens, it stays in solution. But if the lead gets next to iodine, or iodide, anions that come together, they can form PbI2. They're no longer water soluble and they come out. So I can write this in terms of ions. So we're going to call this top one the molecular equation. And we're going to change it to the ionic equation. So we said lead becomes lead 2 plus, and it's an aqueous. And we have 2NO3 minus, that's also a solution. 2Na plus, aqueous. And 2I minus, aqueous. So in terms of ions, that's what we put in our little pot here. So afterwards, we set 2Na plus, aqueous. 2NO3 minus aqueous plus solid, PbI2 solid. So now we've broken everything up into the ions. Now the solid one can't break up in ions because it's a solid. You only have ions in aqueous solution. So that is our ionic equation. Everybody okay with that? We just broke everything apart into ions that can break apart. Well, we can do some cancellations here before I go through the and go with the net ionic. So I can cross things off on both sides that are the same. So do I have a Pb2 plus on each side of the arrow? No. Do I have two NO3 minuses on each side of the arrow? Yes. I can cross those off. Do I have two Na pluses on both sides of the arrow? I can cross those off. Do I have two I minuses on both sides of the arrow? No, so I got to leave that. So whatever's left over, I rewrite. So I have Pb 2 plus aqueous plus 2 I minus aqueous goes to Pb I2 solid. So that's the net ionic equation. That's the actual reaction that's taking place. So what about the sodium and nitrate ions? Okay, they're not doing anything, they're just hanging around there in the solutions. So, if you're at a football game, you're not playing on the field, you're watching, they call you a what? Spectator. Okay, spectator. So the NO3 minus and the the sodium and nitrate ions are called spectator ions because they're just watching, they're not really doing anything. So if I call you a spectator, maybe you're just sitting here watching, you're not doing anything. Okay. So that's called the net ionic equation. Top of this equation, we're having a broken apart sodium sulfate plus barium hydroxide to give us barium sulfate. So everything that can break apart in ions, you break apart. Then you cancel each side, what appears on each side, and then you write whatever's left over. So you have to, first thing you have to do, that's all there was, that'd be pretty easy, but we can't make it easy, so we have to write and balance a molecular equation. You have to predict what's going to happen. Because we're not going to tell you what the products are. Then you write the ionic equation by separating strong electrolytes into their constituent ions. Then you're going to write the net ionic equation by canceling like terms on each side and writing what's left over. So, write the molecular ionic and net equations for the reaction that occurs when aqueous solutions of lead acetate, and there's the formula, and calcium chloride are combined. So when we do this, we're going to start with just what it says, Pb C2H3O22, lead acetate plus calcium chloride. Now they're aqueous solutions because we specify them as aqueous. This is where the states of matter comes in. Well, how do we know what they're going to become? Because I didn't tell you. What you do is you switch the cations. So the Pb is going to come over here. Ca is going to come over here. Well, in this case, it's pretty simple because the Pb, we know, is 2 plus, and the calcium is 2 plus. So we're going to get calcium plus PbCl2. So it's balanced. Okay? So we're fine there. But I didn't write the states of matter for the two products. I have to look at the solubility chart. So the first one, lead acetate, is it water soluble? What about acetates? If you look at that table, acetates are say are they what?
Water soluble.
They're water soluble. Are there any exceptions? Nope. Okay, so we know that's water soluble. So the calcium acetate, calcium acetate is going to be what? AQ is going to. What about lead chloride? We know chlorides are soluble. Is there an exception? What's the exception? Is lead one of the exceptions? Pb2 plus? Oh, so it's not going to be soluble. So lead chloride is going to be what state of matter? Solid. So now we have our molecular equation. So now we're going to write our ionic equation. Everything that has aqueous we're going to break apart into ions. So here we have Pb2 plus 2C2H3O2 minus. Put the aqueous here. There's solution. We add Ca2 plus aqueous plus 2Cl minus aqueous gives us, this is aqueous, Ca2 plus aqueous plus 2C2H3O2 minus aqueous plus, oh, this is solid, so that doesn't come apart, PbCl2 solid. So now we have our ionic equation. Now things that are like on both sides, we cross off. Oh, 2C2H3O2 minuses and Ca2 plus. So what are we left over? Pb2 plus aqueous plus 2Cl minus aqueous gives us PbCl2 solid. Questions? So you write the reactants of the molecular equation. You switch the cations and make sure it's balanced when you switch the cations. This one happened to be balanced, but won't normally always be balanced. Then you break apart all the aqueous ones. You have to figure out which one's going to be water soluble. And then write the ionic equation, then the net ionic equation. So I was going to say, can I erase this? I don't know which objective, so I'll go to. Let me. So it's solutions of NaCl and KBr. What are the products? What did I say to do? Switch the what? Okay, so switch the cations. So what do I end up with? KCl and NABR. What states are they going to be in? KCl. Soluble or non-soluble? Soluble, so it's going to be what? Aqueous. What about NADR? Oh, because yeah, because sodium. So they're all aqueous. So if they're all aqueous, what does that tell me? If I put them together. Does anything happen? No, there's no reaction. So if everything's aqueous, there's no reaction. Just got a big pool of spectator ions just hanging around.
So would that be the answer, or would you put no reaction?
You put no reaction. Unless it asks you specifically to write that. It might ask you to write that. If you're going to write the ion equation, everything would break apart into ions. The net ionic equation, everything would cross off. There wouldn't be any net ionic equation. So everything would cross off, so there'd be no reaction. Because every time you mix two things together, doesn't mean something's going to happen. All right. Acid-base reaction. Strong acids and bases. Bronsted acids and bases. And acid and base neutralization. Are we okay on the whole molecular, ionic, net ionic, electrolytes, weak electrolytes, strong electrolytes, non-electrolytes? Strong acids and strong bases. When we say strong, in chemical terms, we're not talking about the ability to do damage. We're talking about the ability to ionize. Strong acids and bases ionize completely. So there's strong acids, HCl, HBr, HI, HNO3, HCl3, HCl4, H2SO4. Strong bases, lithium hydroxide, sodium hydroxide, potassium hydroxide, all these other hydroxides are strong bases. They ionize completely. HF, which is, okay, you would say, well, it's in the same column as HCl, HI, and HBr. It should be strong acid. It's not, it's weak acid. HF dissolves glass. So you can't keep it in glass. You have to keep it in plastic. In fact, they use it to etch glass. You can buy it at Michael's craft store. However, if you do, I would strongly suggest that you wear plastic gloves because it will eat the skin right off of you. For those of you who are aficionados of Breaking Bad, in the first season episode, they killed some guy, and they told his assistant to put him in the bathtub, and make sure you line the bathtub. This is an old bathtub, old cloth bathtub. Line it with a shower curtain, put them in there, and add gallons of hydrofluoric acid, which would eat them up completely. Well, the assistant did that, but didn't put the shower curtain in there. How's the shower curtain? Shower curtains are made out of plastic. All ceramic bathtubs are made out of ceramic. Ceramic's a type of glass. Turns out the hydrofluoric acid ate the bathtub. So if you saw the episode, for some reason the bathtub was on the second floor. The bathtub started leaking and the whole thing collapsed and the whole thing fell through the floor. Little literary leeway there. And what was left of the body and all the acid fell on the floor, so they were cleaning up that evening. They were dressed in hazmat suits, cleaning up body parts, hydrofluoric acid. So hydrofluoric acid will do a good job at chewing up a body. Why are you always telling us about killing people and chewing up bodies? Okay, sodium hydroxide, the base, on the other hand, will do just the same. Sodium hydroxide is Drano. Red Devil Lime. If you've ever used Drano and gotten it on your hands, it feels real slippery. That's because it's reacting with the fats and oils in your hands and making soap. That's how you make lye soap. Sodium hydroxide and lard. So it will eat everything away. Farmers, in the old day, I don't know if they still do that, cow dies, and what do you do with that cow? You dig a hole with your bulldozer, put the cow in there, and you put lime over the top. Lime is the base, you cover it up, and it eats everything away. So now you know 2 ways to get rid of dead bodies. In one of our earlier textbooks, there was an example, some guy in England, Scotland, one of those UK countries, ended up killing his 2 children. His wife left them. So he hid them in a peat bog. He buried them in a peat bog. Peat bog is very basic. Turns out years later they found them. They'd been completely turned to soap. And they actually showed pictures of these children that were actually now soap.
The bones in it.
What?
The bones in it.
Probably not the bones, but the outside.
So sodium hydroxide will give you a nasty burn. That's what they use to clean air conditioning coils and heating coils when the guy comes out to clean the coils. My father-in-law used to do that, ended up spilling some down the back of his shirt. And his pant flanks, and his boss sent him home to change clothes. By the time he got home, he was burning so bad when he jumped in the shower, he ended up at Chapel Hill Burn Center. Because chemical burns don't stop, they keep going. So, Bronsted acids and bases. Back in section 2.6, we said an acid is something that ionizes to produce H plus ions, and a base is a substance that ionizes or dissociates, in the case of ionic bases, to produce OH minus. That is the definition of Arrhenius. The Arrhenius definition of an acid or base is an acid produces H plus in water, a base produces OH minus in water. Well, yeah, that worked pretty good for a while, until someone said, well, hey, here's good old ammonia. Ammonia is a base. If you look at sodium hydroxide in water, it goes to Na plus OH minus. So there's the Arrhenius definition of a base. This is a base. Where's the OH coming from? There's no O. So something's wrong here. So, Bronsted-Lowry, or Bronsted, sometimes it's paired with Lowry. A Bronsted base is a proton donor, and a Bronsted base is a proton acceptor. Now, proton is called H+, so it's a hydrogen ion. So if I go back here and look at my good old friend ammonia here, and here I have water, we said a base, according to Bronsted, does what? Accepts a proton. So it's going to get an H+. So we're going to add an H, so an H4, and it's plus, it gets plus charge. Well, if I take an H plus away from H2O, what am I left with? Or OH minus. Oh, there's my OH minus. And Arrhenius couldn't account for it. Look at the bottom one, hydrofluoric, hydrogen fluoride, and so in water, we said that acid is a proton donor. So that's going to give an H plus to the H2O, so the H2O is going to become H3O plus. We call that the hydronium ion. That was in your chart of polyatomic ions. So here's where it comes into use. and we're left with F minus. So we're talking about Arrhenius acids, we're talking about H plus. We're talking about Bronson acids, we're talking about H3O plus. So that's a more inclusive definition of acids and bases. So here, it doesn't have to be a solution. Here we have two gases, HCl and NH3. So the NH3 takes a proton to become NH4 plus. The HCl gives up a proton and becomes Cl minus. So now you have NH4 plus, Cl minus. They come together to give us NH4Cl, which is a solid. So if I actually take some hydrochloric acid, which gives off HCl gas, some ammonium hydroxide, which gives off ammonia, just going to get near each other, you'll see this big wave cloud for H4Cl. Most strong acids are called monoprotic. They have one hydrogen that they can give up. Sulfuric acid, H2SO4, are diprotic. So it has two protons it can donate. So how does that work? You start with H2SO4 plus H2O. This donates a proton because it's an acid. So we get H3O plus HSO4 minus. Now the HSO4 minus also has a hydrogen. It can donate a proton to another molecule of water, give us another H3O plus SO4 2 minus. So if we look at the sum of those two and cross off like terms, we can say that H2SO4 reacts with two molecules of water to give us two hydronium ions plus SO4 2 minus. So if I start with equal concentrations of hydrochloric acid and sulfuric acid, sulfuric acid is going to give me twice as much H3O plus than the HCl, because it has two hydrogens that can donate. So it's going to be stronger. Phosphoric acid, H3O, H3PO4, has three hydrogens. So H2SO4, diprotic. Everything above that's called polyprotic, H3PO4. So if you look at sulfuric acid, the first one, is strong. It ionizes completely. The first hydrogen comes off completely. The second one only comes off partially. So it's strong with its first ionization, it's weak with its second ionization. And we get to 152, we'll work out all the numbers for that. Phosphoric is weak all the way, each ionization. The first one is stronger than the second one is stronger than the third one. We really haven't talked about the double arrow and equilibrium, but we'll get to that. And again, don't confuse weak and strong with ability to do damage.
Acetic acid, I told you, is very weak in terms of acid. Concentrated acetic acid will burn the skin right off. Does he do go around testing all this stuff? Yes. So acid-base neutralization. You know, you see it on commercials all the time. You know, take Tums, takes Rolex, neutralizes 1.5 times the acid or whatever. Well, it's an acid-base reaction. It's called neutralization. In general, the reaction produces water and a salt. So if you look at the first one, hydrochloric acid plus sodium hydroxide, again, we're going to switch to cations. Later on, it's called a double replacement reaction because you're just switching both. So we end up with NaCl, which is salt, and HOH, which is water. So if you look at the ionic equation, the second one there, we've separated everything into ions. The bottom one is the net ionic equation. It turned out that really what's happening is the H plus is reacting with the OH minus to give us water. So that's what we do when we take an antacid to neutralize our excess stomach acid. Or, for example, formic acid. Anybody ever get exposed to formic acid? No? You ever get bit by a fire ant? That's what it injects into formic acid. So, it hurts, it's painful, you go in the house, get some baking soda, make a paste and put it on there, you'll neutralize the formic acid. And we'll talk about neutralization reactions later on in the chapter. Do I want to do oxidation number? No, we're going to stop right there. Yay! Okay.